We saw at the end of lecture A that the derivative of revenue with respect to price can be written in terms of the demand function and its derivative in this way, and we get a positive number with this example here, though it could have been negative, for example, if this number were different, or if that number were different. Could have gotten a negative output. On the PowerPoint slide, I've also got this question: what is a condition on f prime that's equivalent to drdp equaling 0? And I'll explain why that's important as well. So here's the RDP here. What's a condition on f prime when that's 0? It would be p times f prime of p plus f of p equaling 0. That equation and this thing equaling 0 would be equivalent to each other. That's equivalent if I subtract f of p from both sides and then divide both sides by p, to f prime of p being the opposite of f of p over p. This has an interesting geometric interpretation that's going to be emphasized if I write this. I'm going to show you an example in Mathematica with a formula with a graph that illustrates why that condition on f and f prime is equivalent to drdp being 0. So the example that I have here involves this demand function. Where did that demand function come from? I just made it up, okay? No practical situation in mind. I was just trying to make an example up where something interesting happened. That's f of p. Based on this is the corresponding revenue. And these L functions are just functions that help me make a pretty graph. What we see here is a graph of the demand curve. Quantity sold is a function of price. It is decreasing. We see some other graphs too. The red line is the tangent line to the graph of f of p at the given black dot. We see a couple green lines in there. What in the world are those green lines? Those green lines have certain special slopes and go through this black point as well. This one has a slope equal to what I wrote over there. Equal to this fraction here. Or excuse me, without the negative sign. Why? It's just rise or run. Not for the blue graph itself, but just for those 2 points. For the green graph with the positive slope. That's the change in y along the green graph with positive slope. That's the change in p. The other green graph with the negative slope has this slope when you include the negative sign. Notice the relationship between the 2 green graphs. They have the same amount of steepness, just opposite signs for their slopes. They're reflections of each other across this vertical black dashed line. What we're after for when drdp is 0 is for when the tangent line, whose slope is f prime of p, has the same slope as the green line with the negative slope, like right around here somewhere. They have the same slope when p is close to 100. And lo and behold, if you graph the revenue function, it's got a maximum at p equals 100, where its slope is 0. It's no accident. And in fact, if you have Mathematica solved when our prime of p is 0, it did happen to occur exactly at 100. I think that's kind of cool, okay? We can give a geometric interpretation for when the revenue is going to be maximized in terms of the demand curve. It's a complicated geometric interpretation. When are the red line and the green line with the negative slope, when are they parallel? Right at 100. It's a geometric interpretation on the demand curve for when you're going to have a maximum revenue based on this equation. I think that's pretty cool. Okay? Kind of complicated, but kind of cool. This is the kind of stuff that gets me really excited. Math comes alive with this kind of stuff. All right. In our time remaining, it's most important for us to get a little practice with a couple new rules. The derivations of these rules are on these slides, but I don't want to take the time to go through them. I will put this in our shared folder, and you can look at it there. And maybe we'll take the time to go through them on Wednesday a little bit. I will say the derivation of this thing here called the quotient rule, there's an extra tricky thing that in this expression right here, we replace dg with 0, but only in the bottom. That's like, why not in the top too? That seems extra mysterious. So yes, this stuff is full of mysterious steps. This is mysterious. Okay, it's not meant to be rigorous. It gets you to this thing called the quotient rule. H of x is f of x divided by g of x, a quotient, fraction. What is its derivative in terms of the derivatives of f and g? It's this thing. Whereas the product rule can be written as left d right plus right d left, where f of x is on the left and g of x is on the right. The quotient rule has a high and a low function. High on top, low on the bottom. F of x is on the top, g of x is on the bottom. The way to memorize the top here of this fraction is low d high minus high d low over the square of what's below. Adding the b. The low makes it flow a little nicer. Low d high minus high d low over the square of what's below. The order here matters. Subtraction is not commutative. I think I mentioned this before. You might wonder, how can subtraction not be commutative when addition is commutative and subtraction really is addition? Well, certainly 5 minus 3 does not equal 3 minus 5. But how does that, how do you understand that in terms of addition? Well, they are different additions. Right? 5 minus 3 is 5 plus negative 3, which does equal negative 3 plus 5. That's all equal to 2. But 3 minus 5 does not equal 5 plus negative 3. It equals 3 plus negative 5, a different addition. That's why you get a different answer, even though addition is commutative. It's a different addition. Subtraction is not commutative, therefore, if you only think of it as a minus sign. Don't switch these around. That's a common mistake. Let's get a little practice with it. I'll do an example, then I'm going to have you do an example. And while you're doing the example, I'm actually going to keep the videotape going, though I will edit it, and when it's on YouTube, it will not be seen. But together, we are going to do this example here together. Let h of x equal tangent of x. That's sine of x divided by cosine of x. That's the definition of the tangent. It's a quotient. We need the quotient rule, this new rule that you're, for the moment, just believing me about, but you can check all this. What's its derivative? What's h prime of x? Also written as d dx of tangent of x. Use this new rule, this quotient rule. Sine of x is the high function. Cosine of x is the low function. The quotient rule says low d high, d stands for derivative, minus high d low over the square of what's below. Cosine is below, so square that. That is the answer in unsimplified form. That would not be good enough for the gateway. You do want to take the derivative of the sine and the cosine on the top. The derivative of sine is cosine. The derivative of cosine is what? negative sine of x. Cos x times cos x is cos squared x. Minus sine times negative sine is plus sine squared x. This is the derivative. But this can be simplified. We have our old friend, the Pythagorean identity. Cos squared x plus sine squared x always equals 1. The top is a 1. The bottom is a cos squared x. That is okay for the derivative of tangent. It's also sometimes written as secant x squared, the shorthand for which is secant squared x. This is something you can memorize for the gateway, but you should be able to derive it just like I did, if necessary, if I asked you to on exam 2, for example. All right, we'll keep the video going, but I'll edit it. Let's have you work on an example for a few minutes. I want you to differentiate this, and I think I do want you to simplify it too. Simplify it. Work on that for a few minutes. So now let's go through the derivative. This is a quotient. There's the high function, there's the low function. Again, don't be thrown off by the fact that this is an f of x instead of an h of x. Use the principle of the quotient rule. The derivative of this quotient is low, fraction, low is the bottom, 5x minus 2. D high means multiply times the derivative of the top. 4x plus 3. I'm going ahead and writing the d dx in there. Though you could just write a forward, simple enough that that would be fine. Minus high, 4x plus 3. Notice I'm using parentheses there. It's really important. I'm going to use it here too. Those are common mistakes people make on the gateways, forgetting parentheses where they're needed. Low d high minus high d low, the derivative of 5x minus 2, which is 5. Over the square of what's below. You can expand the bottom out if you want to simplify it. It would expand out to 25x squared minus 20x plus 4, but that's not a big deal to me. Let's simplify the top though. It's typically, in this situation, more important to simplify the top because it's important to figure out where derivatives equal 0, and fractions only equal 0 when the top is 0. Careful about signs. And make sure you double check me that I don't make a mistake. This looks good. The 20x's happen to cancel here. Negative 8 minus 15 is negative 23 over 5x minus 2 squared. And that tells us something interesting. That tells us the derivative of this function is always negative. It's always decreasing. Function. Is that really true? It's a rational function. It's got a vertical and horizontal asymptote. Horizontal asymptote is 4/5. Vertical asymptote that would be what, 2/5. And x-intercept at negative 3/4. I think it looks something like this. Yes, it's decreasing wherever it's defined. You can check that on your calculator. Its derivative is always negative. That's the quotient rule. You got to get practice with these things, okay? You can't just sit here one day, look at what I did, practice a couple times, and be good enough at it to do well in Gateway. You have to practice these things. The completion assignment due on Wednesday does involve quite a lot of practice with derivatives. It's a longer assignment than the one today. There's another rule called the chain rule that's also very important. For the derivative of a composite function, where you plug one function's output into the other function. Remember that? Composition, the circle operation. F circle g of x means f of g of x. I once again have a derivation of this on this slide, but I think it's more important for us to get a little practice with it. The derivation actually is, in the big scheme of things, fairly short. Here it is, and there's the rule. I don't want to take the time to explain this right now. Again, I think it's more important for us to get practice with it. What does it say? H of x is the composition f of g of x. First of all, f circle g of x. What's the derivative with respect to x, which you could also call dy dx? It's ultimately equal to this. It's equal to f prime of g of x times g prime of x. The derivative of f, the outside function, substitute the inside function into that derivative, that's plugging g of x into f prime, times the derivative of that inside function. And that's the way I remember it myself, is in terms of outside functions and inside function. In the composition f of g of x is the inner function, inside. It gets done first, you work inside out. You take its output and you plug it into the outside function, f. The derivative of that function is the derivative of the outside function, plug in the inside function, times the derivative of the inside function. This definitely takes some practice to get used to. I'll do an example, then I'll have you do an example. I'll do it with an h of x first. And maybe your example, I'll call it f of x, because again, the symbols don't matter, it's the idea that matters. Let's say it's sine of x squared. That's a composition. Do x squared first, then take the sine. The inside function is the squaring function. The outside function is the sine function. This would be f of g of x when f of x equals sine of x and g of x equals x squared. So its derivative by this formula is f prime of g of x times g prime of x. F prime of x is cosine of x, and g prime of x is 2x. Now just substitute. F prime of g of x is cosine of x squared. G prime of x is 2x. There's the answer, which you can also write as 2x cosine of x squared.
Is there a mistake on the slide then? Should that g of x?
Yes, that's a mistake. Thanks for catching that. Oh, I can't write on the wall. Okay, yes, there should be a prime here. Thanks so much for catching that. Okay. Definitely a mistake there. What's on the board here is correct. All right, let's have you do an example. And again, we'll keep the video going and I'll edit it. And I am going to go ahead and call it f of x. Don't be bothered by that change. Let's actually do it the other way around. Let's do sine squared of x, which recall really means sine of x squared. Work on that one now. It's a different function. It's got a different derivative. All right, so you should have gotten the answer 2 times sine x times cos x. The answer. If you're thinking purely in terms of the words outside function and inside function, the outside function here is the squaring function. The inside function is sine of x. The derivative of x squared is 2x. Bring down that 2. But then you got to plug in the inside function into that. This is like 2x except replace x with sine x. Times g prime of x times the derivative of the inside, the derivative of sine is cosine. And you can write this without those parentheses. You can write 2 sine x cos x. If you want to be more careful about it, if you're feeling unsure, you could use the letters g and h over here. You could say this is g of h of x. So I'm switching around the roles of these function names, where g of x is the outside function, that's x squared. H of x is the inside function, that's sine of x. G prime of x is 2x. H prime of x is cos x. The chain rule says f prime of x would be the derivative of the outside function, plug in the inside function, times the derivative of the inside function. G prime is 2x. Replace its input with h of x, which is sine x, times h prime, which is cosine. Okay? For some people, when I just did that, that went by too fast for you. I went by fast because I already do one more example. You got to practice to get fast at it and accurate. Okay? You can't be successful at this stuff without practice. Let's do one more example. Why don't we even do one where we have to combine a couple of rules? F of x equals x e to the x squared. At the most fundamental level, this is the product of two functions. A first function, a left function and a right function. Product rule says lefty right plus righty left. Left d right plus right d left. If this is new to you, you're going to want to write that out. When I take the derivative of the right, I need the chain rule as well. Because there's an inside function x squared and an outside function e to the x. This is the composition. The derivative of e to the x is itself e to the x. Plug in the inside function into that, which is x squared. Then multiply times the derivative of the inside function, which is 2x. The derivative of x is 1, so you get this. There's the answer. It can be simplified. You can write this as 2x squared e to the x squared. If you like, you can factor out an e to the x squared and write it as e to the x squared times, in parentheses, 2x squared plus 1. In general, that might help you figure out where this derivative is 0, though for real values here, this derivative here is never 0. It's always positive. The graph of that function is always going up. Yeah, I think it probably looks something like this. Probably looks like that. Kind of looks like a cubic, I think, though it's going to grow faster than a cubic. Okay, you got to practice. Make sure you practice on your homework. And check your answers with Mathematica and with graphs. Okay? See you Wednesday.